Hello everyone, this is Ashish and today I'm going to discuss one of the most common interview questions for mechanical engineers, aerospace engineers, sometimes even civil engineers. It is related to strength of material or mechanics of solid or solid mechanics, whatever name you know it by. It's called the stress strain curve. Now there are levels of interviews, and in a lot of interviews which might not require that much technical work or research oriented work, they just might ask stress strain curve to test if you know anything about engineering where you have spent 4 years of your time. But in jobs that I applied for example Bhabha Atomic Research Center, Indian Space Research Organization, or for research profile masters in Indian Institute of Technology, these kind of interviews where your role is supposed to be research oriented in R&D, they will be expecting you to know not only what is stress strain curve but why it is that way. So without wasting any time, I'm going to start explaining it over here. So engineers often do this kind of experiment in college. There's a specimen with certain diameter, and also if you want to go more detail, the specimen is broader along the ends specifically to hold it in the universal testing machine. Our main focus over here is what is going to be the stress strain curve. So the machine in which you are going to put it, that machine does not give you the stress versus strain. If you do not know, that machine gives you a load versus displacement. That is what that machine is calculating. But ultimately that is not going to help us, because what we are trying to do over here is to find out the ultimate tensile stress, which also is a uniaxial state of stress, because we are applying load only in one direction, and that is also parallel to the axis of the element. So it is a uniaxial state of stress. You can call it sigma x, saying that this is x direction, which is kind of counter to your general convention, but let's say that's how it is. So we are applying load only in one direction. So this is one dimensional axial stress. There are two kinds of stresses in total: axial stress and shear stress. Compression and tension both are axial stress. Shear stress is different because their force is parallel to the surface. So let us say this is my surface, force is parallel to the surface, that's shear stress. Force is perpendicular to the surface, that's my tensile stress. Area is also a vector, force is also a vector. The relation of these two vectors' directions matter. But it is much easier to just do one test in which we are going to put all the materials in a simple uniaxial loading. And the properties that we get from that loading can be used using the principal stress ideas and the theories of failure to find out the failure stresses, critical points for all the different loading scenarios. Now, this is my engineering strain and this is my engineering stress. And that's another mistake a lot of people do. They just say that, oh, this is stress, this is strain. But there are two kinds of stresses, there are two kinds of strains. There's engineering stress and then there's true stress. There's engineering strain and then there's true strain. And I think in high level R&D job positions, this is what creates the difference. Like a random just graduate who has studied mechanics of solid like 3 quarters ago will just say, okay, this is stress, this is strain. But someone who is research oriented, who has studied books, has understood the concepts well, will be mentioning these tiny things. And also never make an axis without these arrows. It's just disrespectful. Now, when the force is 0, the stress is 0, and at that time strain is 0, there's no displacement. So we are going to definitely start from this. Now I'm just going to use a straight line for this one because it is very important, and this is something everybody knows. This is the proportionality limit. It is also within the elastic limit, and yes, there's a difference in between those two. But the main point is that it's a linear graph. Now we get a lot of things out of it, and the one most commonly known is the Young's modulus. Now Young's modulus is equal to stress by strain, but where? Within the elasticity region. Over here I've written stress by strain because in fact the engineering stress and true stress are same. But where did it come from? And it came from Hooke's law. And Hooke's law did not say that E is equal to sigma by E, or it did not say that sigma is equal to E into strain. It just said that stress is proportional to strain. And by saying that, we know that if there's any proportionality, that can be converted into equality by adding a constant of proportionality. And so we are going to say stress is equal to some constant, which is constant of a material, multiplied by strain. And as you know, at any point, the slope of this is going to give the ratio of stress by strain. That is why slope of this straight line is equal to Young's modulus. The point till which the stress is directly proportional to strain, or the stress strain curve is linear, is the proportionality limit. But one thing I want to mention over here is that some people also put another limit over here, which is called the elastic limit. Here's the thing, elastic limit and proportionality limit most people will consider as the same, but if you really want to know the difference, it is explained very well by the name itself. The proportionality limit will be the limit till which the stress is directly proportional to strain, or in other terms the graph is linear, and the elastic limit will be the point till which the material, if unloaded, will reach back to its original shape and size, but it is not going to follow a linear curve. So if, say, you load a material and the stress is increasing and the strain is increasing, and at this point somewhere you decide to remove the load, the material will reach back to the origin from where we started. But beyond this point, you're going to witness an upper yield point and a lower yield point, and beyond this you have reached the plastic region. And if the material is unloaded somewhere over here, you are definitely not going to come back to its original shape and size. Some deformation will be retained by the material. So that's a minor thing that I wanted to add over here. I missed it in the first time I was doing this video. There's a minor difference, but from now on we are going to consider this as the same point. A tiny detail over here is that during the elastic deformation, the volume of the body does not remain constant, and that is because the bond gap itself changes during the elastic deformation. The bond elongates, so you're actually going to see like a increase in volume in a very minuscule level. But in plastic deformation, volume remains constant, and when you remove the load, it is not going to come back. Before you start making the diagram, you have to mention which metal or material this stress strain curve is for. And the reason it came into my mind now is because most of the material will be having similar curve till this point, till proportionality limit, but after that it is different for different materials. So right now what I'm going to do is that I'm going to say that I'm right now drawing for mild steel. For mild steel, what you're going to see is that a dip over here, and this is something that I want to explain later. Then you are going to see something called Ludus band. It is also called stretcher strain. Beyond this, you are again going to see an increase of stress for the increase of strain, and then it is going to face this dip. Now till this point, the engineering stress strain curve is same as the true stress strain curve, but this is where it differs. This is going to be your true stress, and this is going to be your engineering stress. Why? Because true stress is force divided by area at that particular instant. So I'll just put I over here. But engineering stress is much simpler, and that is force per unit original area. So the original area is same, right? So at this point, this was the original area. I'm just going to keep on dividing all the different forces that I'm going to get from the load displacement reading of the universal testing machine. I'm just going to keep on dividing by original area. So that remains constant. The force changes, and this is how it changes. But at some point, necking is going to start. That means the material is going to start to show something like this, right? Before anything breaks, there's probably some decrease in cross section. At some point it can't withstand and it breaks away. So the area over here is decreasing. So that's what's happening over here. So over here, the force required kind of decreases, but the area dramatically decreases, and because of that the stress actually increases, and that's the true stress, and this is the engineering stress. But this is what you will be seeing in most of the places. These are the things about the stress strain curve that most people don't know. So we have gotten some interesting points which will turn out to be important properties for us. One of it so far is failure stress, or you can also say ultimate stress, but please don't call it fracture stress. This is not your fracture stress. This is the point where the necking starts, but this is not the point where the fracture starts or fracture happens. This is the point where the fracture happens. This is your upper yield point. This is your lower yield point. This is the point where the necking happens. And this is the most important point. This is basically the strength of our ductile material, the point at which it starts to basically fail and breaks. Like once that point is reached, 100% it's going to break, because it is going to continue to have the load, so it is going to break. And this is you can call fracture point. Let's redraw the stress strain curve for mild steel. You're going to have something like this. A lot of people even skip this. They directly go from here to the strain hardening region, which I'm going to explain soon. So this is how your stress strain curve is going to look for a mild steel. That is one proportionality limit. Some people call it same as the elastic limit. I won't blame them, and I'm going to do the same over here to simplify things. This is your sigma y1, that is your upper yield point. This is your sigma y2, that is your lower yield point. There's no specific name for this, but you know, sigma y2 will also be equal to the stress that is at this point. So this is a interesting region because there's deformation without actually the load changing. So you're not increasing the load and the deformation just keeps on happening. So it's also kind of like a fluid flow. The load is constant, but deformation continues the way that it happens in fluids, which is a topic for another day. And this over here is your ultimate stress, and this over here is your fracture stress. This does not matter at all. All right, once you are here, you're done. So you're going to check mostly for your sigma u. So this is your mild steel. I'm going to write mild steel over here, and then I'm going to use a different color, and this time I'm going to draw for cast iron. Now for cast iron, it is going to look something like this. This is your cast iron, and that's pretty much about it. It is going to fail somewhere over here. I'm going to zoom a little bit because the next one is going to be even smaller. Few things that you have to pay attention towards. You should draw it within and not outside. You could have drawn it like this as well. See, the basic idea of cast iron being a straight line and failing somewhere over there is because cast iron does not show a lot of plastic deformation. Cast iron comes under the category of brittle materials. They just fail without any warning. You're going to keep on loading it. You're like, oh, we're good. And then all of a sudden it's gone. It breaks. It fails all of a sudden, like glass, cast iron, or other brittle stuff, man. Google it. Why I have drawn it within is because cast iron has Young's modulus close to 100 gigapascal, and these little quantities, I think it is important for you to know. Sometimes they say, oh, what do you think is the Young's modulus of cast iron? And you say, I don't know, I don't mark things up, bro. I understand things, I'm a conceptual guy. But what the interviewer is trying to ask is that, do you even know the ballpark? Is it like 10 megapascal or 100 megapascal or 100 gigapascal or 100 pascal? What do you think it is? So Young's modulus is generally, like most of the time, in gigapascal. Ultimate stress, yield stress, and all of these fracture stress, these are all always going to be in the range of megapascal. So for cast iron, you're having E as 100 gigapascal, and for mild steel, you're having E as close to 240 gigapascal. That is why, as you can see, what Young's modulus ultimately gives you is the slope, right? So you're having more stress per unit strain. So you're going to have a steeper curve for mild steel, a shallower curve for cast iron. Some interviewers might even be happy if you just show a straight line over here. Some might not be. Now, obviously, the tensile strength of mild steel is going to be much higher, and it's 400 megapascal. Because you see, it can actually plastically form a lot, and in doing so, it takes a lot of load, right? So this would be somewhere close to like 140 or so, and this is close to 400, and according to this, it looks pretty good. Now aluminium is going to look something like this. Now this is how aluminium looks like. So as you can see, aluminium is ductile too, but you're not seeing the yield points, you're not seeing the stretcher strain, you're not seeing anything over here that you are seeing in mild steel. It's a completely different one. And if you want to know, this is where the necking for aluminium would happen. But this is again, your stress is proportional to strain region, and for aluminium, your E, Young's modulus, comes in the range of 69. Ultimate stress 310 megapascal. And it does not really fit well, because if this is 310 megapascal, this cannot be 140. So let us say that our cast iron actually was just until this point or so. So this is the most like accurate way of drawing the 3 stress strain curves when your interviewer asks you to. You can do any random stuff, and a lot of times for small interviews, even the interviewers won't know, but this is attested. This is how you're supposed to do it. Now, we did not even discuss why the mild steel behaves the way it does. There are also a few questions. Okay, let me answer one question very quickly. The interviewer will say that, oh, then how are you going to decide the yield point of aluminium? And it's very simple. Just use the concept of what we call proof stress. And proof stress is 0.2% of the deviation, and that a lot of people don't understand what it is. In every specimen material, it will have certain length, and you should take the 0.2% strain according to that length, and that you plot over here, and then draw a line parallel to the line of proportionality, or draw a line with the slope of E, in this case 69, and then wherever it intersects with the curve, that's your yield point for aluminium. Simple. But yeah, this 2.2% is not as simple as most people think, and I've even seen a lot of people not even doing it properly, just taking anything like 2.2% and having a line a little bit on the offset. But yeah, it has to do with the length of the specimen, and again, most of the time the specimen is a standard specimen and the length is also fixed. So this is a common question: how are you going to find out the yield point? Yield point is also important because that is essentially the point past which plastic deformation starts to happen. So yield point is important, and over here you don't even see any clear demarcation or proportionality limit. So yield point is very important for a material which shows such a bogus stress strain curve as aluminium. I don't think I will be able to explain why the mild steel stress strain curve behaves the way it does, but I think we can carry it over to the next one. See you over there. And if you like such kind of explanations, let me know. I can do more of that. I have like 10 years of mechanical engineering inside this tiny head. I can open it up every now and then, boy. Alright, read my book, The Boy Who Did Not Science, a fictional book inspired by my journey in nuclear program and working towards getting into space program, both scientist positions. Okay, see you next time. Till then, bye.